Hello everyone, welcome to my YouTube channel Mathematics Made Easy. So in today's video we have this problem from abstract algebra groups theory. So the problem is, if H is a subgroup of G and X is an element of G, so say let K be equal to xHx inverse, which is equal to small x inverse, such that H is an element of big H. So I have to show that K is a subgroup of G, and then if H is finite, so what is the order of K? Alright guys, so before we dive into the solution, please don't forget to subscribe to my channel, like my videos, comment, and then also share. Now the first thing is to show that K is a subgroup of G. Then what are the criteria for K to be a subgroup of G? The first thing is that K must not be empty, okay? Then the closure property must be satisfied, and then there must be an inverse for each element in K. That is, all elements in K must be invertible for K to be a subgroup of G. Alright, let's start with the proof. So the first one is K must not be empty. Yeah, obviously K is not empty. Then how can we prove that K is not empty? Now, we know that the identity element is in K, alright? The identity element is in K, so K is not empty, okay? Such that K is equal to X, the definition of K is xHx inverse. So let H be E, which is the identity element. So you have XE, X inverse. So don't forget, if you combine the identity element with any element, you are going to have that element. So we have xx inverse, and xx inverse will give us what? The identity element, which is also in what? Which is also in K, okay? So K is not empty. K is not empty. We are done with that. Now let's check for the closure property. Alright, the closure property. So we can say let A, B be an element of K. Alright. Then there exists H1, H2 in what? In big H. So such that A will give us, we said K is equal to xHx inverse, okay? So, and then we already said that A and B are from K, okay? And H1, H2 are from H. So we can now say K, which is now A, is equal to xH1 X inverse, alright? And then we can say B is equal to xH2 X inverse. Alright, beautiful. Now, to show whether the closure property is satisfied, we have to combine A and B, okay? That is, AB will be equal to xH1 X inverse, okay? Combining with xH2 X inverse, alright? So this is gonna give us AB, which is equal to xH1, okay? So x inverse x, then h2 x inverse, alright? So we have AB is equal to xH1 h2 x inverse. How do we get this? X inverse and x will give us the identity element, okay? So we combine the identity element with any other element, you are still going to have that element. The definition of identity element, AE is equal to EA, which is also equal to what? A. So that's what happened here. And then we know that H1 and H2 will be from what? Will be from H, okay? So since H is a subgroup, then H1, H2 is also in H. That shows that the closure property is satisfied. Hence, AB is in K. Alright, AB is in K. Since we have H1 and H2 here, which is in H, then AB will also be in K. So we are done with the closure property. So the last property to check whether this is a subgroup is the inverse. Okay, so we can say let A be an element of K. Alright. So don't forget the definition of K, which is xHx inverse. So we can now say A is equal to xHx inverse. Now, for some H in big H, alright? For some small h in big H. Now let's find the inverse. So we can now say A inverse is equal to xHx inverse, then everything inverse. So we have A inverse is equal to x H inverse x inverse. All right. So since H is a subgroup, then H inverse is also in what? Is also in H. Therefore, A inverse is an element of K. Now, since these three properties are satisfied, so we can now boldly say that K is a subgroup of G. All right, moving on, we have to prove that H is finite. And then if H is finite, what will be the order of K? All right, let me change the ink of the marker. All right, let's use blue. All right, guys, so let's do that now. So they say if H is finite, what will be the order of K? So how do we do that? All right, let me write out the question. If H is finite, then we are to find the order of K. All right, now let's define a map. Define the map such that phi is taking an element from H to K. Okay, then phi of H is equal to xHx inverse. All right, now the first one, how do we check or how do we know the order of K? Now we have to check for the bijective property. And how do you check for the bijective property? You know, the injective property must be satisfied and the surjective property must be satisfied. Okay, if the mapping is both injective and surjective, then we said it is what? It is bijective. All right, now let's check. Now let's check for the injective property. So phi is injective. Let's check whether phi is injective or not. Okay, so phi of h1, so let h be equal to h1 now. So phi of h1 will be equal to phi of h2. So this implies that xh1 x inverse, don't forget phi of h is equal to xh x inverse. Okay, so phi of h1 will be xh1 x inverse is equal to phi of h2 will be xh2 x inverse. All right, so if we multiply the right hand side by x inverse and the left hand side by x, so we are going to have x inverse xh1 x inverse, then x inverse is equal to x inverse into xh2 x inverse, then multiply by x. Sorry, this is x, not x inverse. All right, so this and this we join using the associative property. So x inverse x, then we have h1, then this and this also we have x inverse x, which is equal to associative property. We apply here x1 x, x inverse x, then h2 x inverse x. All right, so this will give us the identity element. Then we are going to have h1, this also will give us the identity element is equal to h2. So that shows that the injective property is satisfied. So phi is injective. All right, now let's check for the surjective. So phi is surjective. It's subjective, obviously. It's surjective. You know, by definition. So every element of K, has the what? Is from what? Every element of K is from xHx inverse. Okay, for some h in H, then phi is surjective. All right, now since the bijective property is satisfied, then the cardinality, or you say the order, all right, or the order, since phi is a bijection, then the order of K is equal to the order of H. Then that completes the proof. And then this subgroup is generally called a conjugate subgroup. And then a conjugate subgroup usually have same order. So that is that about that. Okay, so if you like this kind of video, please don't forget to subscribe, like, comment, and also share. Thanks for watching. See you next time.